We've already learned that exponential equations and logarithmic equations are inverses of each other. It seems only reasonable that the properties of exponents and the properties of logarithms are related to each other. Let's take a look at this first property. It's the log containing a product. Notice how that product on the left turns into the sum of two separate logarithms. We know in exponential form, if we have something like x squared times x to the third, that is a product, that turns into the sum of the exponents, in this case x to the fifth. In property number 2, we see that the log of a quotient turns into subtraction of two separate logs. Well, we know that if we have something like x to the 7th divided by x to the 5th, which is a quotient, we can subtract exponents and have x to the 2nd. So these are very much related to each other. We have a power in this next logarithm, which can be brought out in front, multiplied by the rest of the log. That's the same thing as having x to the 2nd raised to the 5th power. A power raised again to a power says multiply exponents. We get x to the 10th. Now those are the three basic properties that we use most frequently. There are 4 additional properties I'd like to take a look at. And I'm going to show you how these work and how they're related by converting them into exponential equations. Notice on property of 4, I can say a to the 0 power is equal to 1. We know that anything to the 0 power is equal to 1. So any time we take the log of 1, the answer must be 0. Likewise, in property number 5, a to the first is equal to a, which you know is a true statement, and this tells us that any time the base and the argument of the logarithm are the same, that log is going to equal 1. Properties 6 and 7 are a little bit more challenging to see. Basically, we have an exponential expression being substituted into a logarithmic expression, with the base of the exponential equation the same as the base of the logarithmic function. Now we know that when we have inverses, f composite f inverse of x should equal x. In other words, we know that functions and their inverses undo each other. And basically what that says here is, whoop, out pops the x. Likewise, if you have a logarithmic expression substituted into the exponent position, a to the power, you're doing the same thing, but this time it's like saying f inverse composed with f of x is equal to x. Out pops that x, and that's what it's equal to. Now let's use properties of exponents to write these as separate simplified logarithms. Inside this argument, we have both multiplication and a power. Let's split the multiplication into addition. This tells us we'll have log of x plus log of y squared. Now, that's not quite simplified. I can bring that power out front using property number 3, and this will simplify to log of x plus 2 logs of y. For number 2, we see a quotient, and that turns into subtraction. So we will have the log of the square root of x minus the log of yz. Now that square root we can actually think of as being a 1/2 power, which can be brought out front. And so that turns into 1/2 log of x minus, and this is where we sometimes get into some trouble. People see multiplication and they want to write log of y plus log of z. But all of it is being subtracted, so technically we need parentheses around here, and we need to distribute that negative. This will give us 1/2 log of x minus the log of y minus the log of z. And if you think about it, we're dividing by both y and z, so both the logs with y and z should be subtracted off. Now let's go in the other direction and write this as one single simplified log. This first log is simplified already, but we've got a 1/2 power I can bring up on the second log, and I have a third power I can bring up on the third log. This can be rewritten as log base 5 of a minus log base 5 of the square root of b minus log base 5 of c cubed. Now what I can do is I can, because I've got the same base in all of these, write this as a single log. Log base 5 of. Well, a will be in the numerator. We're subtracting these other two logs, so root b and c cubed will both be in the denominator. When we go to simplify this next expression, the subtraction between the two logs tells us we're going to have a quotient. So this will become log base x of p squared minus 4 divided by p minus 2. Now you notice that that numerator is the difference of two squares, so we can factor and cancel inside this argument and rewrite this instead as log base x of just p plus 2. Let's do one last problem where it's kind of a fill-in-the-blank problem. What should be in each of these blanks? Here in problem A, both of these are log base 4. We've got a 3 and the 7. When we add two logarithms together, we take the product of their arguments, and so this should be a 21 inside that blank. We have subtraction in this next case. 8 divided by 9 makes this 8/9. Likewise, this 2 on this third property can be brought up as an exponent. We can have 5 squared, which is 25 to fill in that blank.